Let's do an example where we add acid to a buffer. Just a reminder that any acid that we add is going to react with the base component of the buffer. So in this question we're asked, what is the pH of a buffer made from 0.80 molar lithium fluoride and 0.80 molar HF, where the Ka is 7.1 times 10 to the negative fourth, after we add 10 milliliters of 2 molar HCl to 1 liter of the buffer? The initial buffer's pH was 3.15. So we want to see how is the pH going to change. All right, so the first thing we need to do is we need to figure out how much hydronium ion is going to be added. Because when we add HCl, HCl is a strong acid, which means it fully dissociates. All right, so that means that we're adding H3O plus that we can easily calculate given the molarity and the volume of that HCl. So the H3O plus, the hydronium ion that we add, comes from the molarity of the HCl times the volume divided by the total volume. So that's 2 moles per liter times 10 milliliters, or 0.01 liters. And then we divide that by the total volume, so that's 1 liter plus 10 milliliters, or 1.01 liters. So the amount of H3O plus hydronium ion that we added is 0.0198 molar. Now, we're going to do the chemistry. All right, the base component of the buffer is the fluoride ion, and the hydronium ion that we add will react with that base. We're going to produce water and our HF. Now, this was already in the buffer initially, right? Its concentration was 0.8 molar, and the fluoride ion was in the buffer already. Its concentration was 0.8 molar as well. The hydronium ion that we add is going to fully react with the base. So in other words, this is going to go all the way down to 0. Now, if this goes down by 0.0198 moles per liter, this will also go down by 0.0198 moles per liter. And if this goes down by 0.0198, this side will go up by 0.0198. Water is the solvent, so it's not participating in the equilibrium, it's a liquid. So we add 0.0198 to the product side, we subtract it on the reactant side. And now we use the Henderson-Hasselbalch equation. pH is equal to the pKa plus the log of the anion over the weak acid. All right, so the pKa comes from taking the negative log of the Ka, so the negative log of 7.1 times 10 to the negative fourth, that's our pKa. And then when we do this arithmetic, it comes out to negative 0.02. So when we add those two together, we get 3.13. The initial pH of the buffer was 3.15. It went down to 3.13. We would expect the pH to go down for adding an acid, but because the pH went down so little, we can conclude that this was an effective buffer.